there! Welcome to Up and Atom. I'm Jade. A good scientist achieves the point of view of no one in particular. These were the words of the astronomer Arthur Eddington, whose physics experiments helped verify Einstein's general theory of relativity. We value science because of its objectivity, its ability to remain unbiased and impartial. A good scientist doesn't let their own personal fears, hopes, or expectations interfere with their work. This quality of objectivity is the reason science has a special authority over society. We stop smoking because science says it's bad for us. We believe we've detected the Higgs boson even if we don't understand the academic papers written about it. And we try to cut our carbon emissions because science says it will help stop global warming. But if science really is objective, how do you explain this? In March 2020, scientists in Europe didn't know much about COVID-19, nor did governments. Yet they had to make a choice between two possible strategies for handling the pandemic. Choice 1 was suppression. The goal of this strategy was to minimize the spread of COVID-19 across all communities, from the most vulnerable to the least vulnerable. The idea was to use population-based interventions like lockdowns, face masks, and social distancing. Choice 2 was mitigation. The goal of this strategy was to avoid overwhelming hospitals. Public health interventions were limited to the most vulnerable, like the elderly, while transmission was allowed among the least vulnerable, like young adults. In the beginning of the pandemic, many countries, like the UK, opted for the mitigation strategy, with Boris Johnson warning Brits to prepare to lose loved ones before their time. But then, on March 16th of 2020, the COVID-19 response team at the Imperial College London published a shocking report. The report included a model stating that a suppression strategy would have saved hundreds of thousands of lives. The first author was Neil Ferguson, a professor of mathematical biology at the Imperial College, leader of the Imperial College COVID-19 response team, and at the time, a member of the British Scientific Advisory Group for Emergencies, aka SAGE. The paper caused a sudden U-turn in the UK government's response to COVID-19 and influenced many other countries, such as the US, France, and Germany, to follow suit. But there was one noticeable exception: Sweden. The Swedish scientific community harshly criticised the Imperial College's model. One of the main critics of the model was Johan Giesecke, Professor Emeritus at the Karolinska Institute of Stockholm, epidemiologist at the World Health Organization, and back then, current advisor to the Public Health Agency of Sweden. Giesecke claimed that the Imperial College's conclusion was wrong and that suppression was not the best strategy. Sweden stuck to mitigation. If science really is objective, how is it that two super well-known, well-respected, and multi-award-winning scientists can end up disagreeing with each other? They were presented with the same evidence and were both following the scientific method. Well, let's see how a scientific disagreement even arises. In the beginning of the pandemic, scientists knew very little about COVID, and the evidence available to them was mostly the hard data coming from China and Italy. Data such as COVID's fatality rate and the proportion between infected and recovered people. Maybe because they were scarce, maybe because they were not very reliable, these data seemed suitable to more than one interpretation. This isn't a rare phenomenon, quite the opposite. It happens so often that philosophers of science have coined an expression especially for it: underdetermination. Underdetermination refers to the problem that often more than one theory is compatible with the evidence. Suppose we're two scientists who have just performed a study and collected some data points. We agree that all the data points we have are genuine data and not outliers or artifacts. The X and Y axes represent the two factors we're interested in. I think that these points support the hypothesis that the relation between X and Y is a linear one, whereas you think that the relationship between X and Y is more complicated. There's a mathematical theorem called the interpolation theorem, which proves that there are not only many, but infinitely many curves that can fit a set of data points. The 3 points underdetermine the shape of the curve, and therefore the scientific hypothesis that fits them. Now you might be thinking, but this is just because we have only 3 data points. Scientists collect way more data than that. Your analogy is flawed, Jade. And you're right. Usually the datasets of scientists are way larger than 3 points. But this doesn't completely solve the problem. Assume we add a 4th or 5th point, and these new points happen to all fit the straight line. Maybe one or even both of these curves will be shown to be incorrect. The problem is that there will still be an infinite group of other, more intricate curves that are compatible with the extended set of data points. So even if we collect more data, the evidence is still suitable to more than one reasonable interpretation. The point of all of this is, sometimes the evidence can support 2 hypotheses that are incompatible with each other. So when this happens, how do scientists choose between them? According to the physicist turned philosopher Thomas Kuhn, scientists choose one hypothesis over another according to how well it fares with respect to a list of scientific criteria. These criteria are the characteristics of a good scientific theory. Some of them are accuracy, broad scope, and simplicity. A good scientific theory needs to agree with the experiments and observations. A theory that predicts phenomena that never occur in real life is completely useless. The theory should also extend far beyond the particular observations, laws, or sub-theories it was initially designed to explain. We want to make connections with other topics in the field, and ideally with other disciplines as well. And finally, the theory needs to bring order in our knowledge and unify phenomena that were previously isolated and confused. These are just a few criteria for choosing the best scientific theory. So if all we need to do is choose the theory that best fits the criteria, why do we end up with wildly different, even conflicting theories? Well, different theories fare differently with respect to these criteria. For example, hypothesis A might be easier to work with than hypothesis B, but hypothesis B might make more accurate predictions. Although these criteria are universally shared in the scientific community, scientists can weigh them differently. I might care more about simplicity, for example, while you think accuracy is more important. As a result, scientists can come to disagree about which theory is better, or over which hypothesis to choose. History is full of disagreements stemming from scientists assigning different weights to different criteria. About 100 years ago, there was a huge disagreement between chemists and physicists over whether or not atoms existed. The idea that all matter is made up of tiny atoms had been around since the 4th century BC, when it was first put forth by Democritus, the laughing philosopher. But it made it as a scientific theory only in 1808, with the English chemist John Dalton. Dalton didn't provide any direct evidence for the existence of atoms, but instead he showed how the idea of them shed light on some otherwise puzzling physical phenomena. For example, it was known that the atmosphere was composed of at least 2 different gases, oxygen and nitrogen. Because oxygen is heavier than nitrogen, it should form a distinct layer at the bottom and the nitrogen gas should be at the top. But this isn't what we see. Instead, we see the atmosphere as a big uniform mass. Dalton argued that the existence of indivisible microscopic particles that rearrange themselves when oxygen and nitrogen react was a simple explanation that resolved the issue. Less than a century later, the entire field of chemistry relied on atoms to make sense of their field, considering them a fact of nature. But physicists remained skeptical. They believed that for something to count as a scientific theory, it needed experimental evidence. They wouldn't accept the theory of atoms without further proof. They claimed that atoms were pictorial representations that one should not take literally. Kuhn's theory about differing criteria sheds light on this disagreement between chemistry and physics. In the 19th century, most of the progress in chemistry was based on atomic theory. Drop the assumption that atoms exist and it becomes very hard, almost impossible, to make sense of a chemical reaction. Unsurprisingly, the fruitfulness of the theory was very much valued by chemists. On the other hand, 19th century physicists cared more about direct evidence. Chemists had not seen atoms, nor were they in a position to measure them directly. Without that, physicists were still unsure about whether atoms existed. Lack of direct evidence trumped fruitfulness. So what do we do when we have these kinds of disagreements in science? We can't really have a to each their own attitude about what matter is made of, or what to do when thousands of lives are at stake. That would completely invalidate the authority and value of science. In the ideal case, we keep exploring, investigating, collecting data, and trying our theories with the hope that at some point we'll be able to reach a consensus. This is what happened with the chemists and physicists. With his theory of Brownian motion, Albert Einstein calculated how a very small but still visible particle would behave if it was bumping into unseen atoms. A while later, a French scientist, Jean-Baptiste Perrin, performed the experiment put forth by Einstein, and the two together provided the direct evidence for atoms that physicists were seeking. I've made a video about that experiment, which I've linked in the description if you want to take a look. A lot of disagreements in science end like this. As evidence builds, scientists find a way to agree and a consensus emerges in the community. But what do we do when we don't have the luxury of time on our hands? With the COVID-19 case, we couldn't afford to wait around for more data while thousands of people were dying. A decision needed to be made. Fast. Well, there's no rulebook for this situation. In these cases, there seem to be further unspoken criteria guiding the choice of scientists, separate to those put forward by Quinn. According to some philosophers, these further criteria are contextual and depend on the scientist's values. They can be ethical, social, political, environmental, aesthetic, and so on. A scientist may lean toward a hypothesis because they think it would help people in poverty, a socio-political value. Or they may decide to embrace a hypothesis because it's in some sense elegant, a cognitive aesthetic value. When the decision isn't clear, scientists sometimes let their own subjective moral judgments sneak in to guide them. Now, I want to be clear. I'm not saying that we shouldn't trust science or scientists. Science is an enormously successful human enterprise. I just wanted to point out some specks of grey in an area that is usually thought of as black and white. Being aware of our biases makes us more equipped to eliminate them. As Jules Verne said in his book, Journey to the Centre of the Earth, science, my boy, is made up of mistakes, but they are mistakes which it is useful to make, because they lead little by little to the truth. Now, I'd like you to take a moment to think about your own values. Would you let them interfere with a scientific judgment? Do you want to help save the most lives? Improve conditions for humanity as a whole? Maybe you want to keep the environment stable for future generations and think working on climate change is the most important thing. If you've ever thought about how you can make a positive impact in the world while enjoying a fulfilling career, I'd like to tell you about today's sponsor, 80,000 Hours. 80,000 Hours is a non-profit that aims to help people have a positive impact with their career. And they're completely free. They actually just want to make the world a better place. You have 80,000 hours in a career. That's 40 hours a week, 50 weeks a year for 40 years. Imagine the amount of positive impact you could make with all of that time if you just knew where to focus it. 80,000 Hours has spent the last decade researching the world's most pressing problems, as well as the key elements that make a career fulfilling. They'll help you with hard questions like, where should I work if I actually want to make a positive difference in the world? What are the most pressing problems facing humanity today, and how might we solve them? What can I do today to start planning a fulfilling career? On their website, 80,000hours.org, you'll find all of their research and guides about how to have a high-impact career, including articles about the world's most pressing problems, career reviews to help you choose the right career for you, and decision-making tools. They also have a podcast where they have unusually in-depth conversations with experts in the world's most pressing problems and what you can do to solve them. Everything they provide is completely free. They're a non-profit, and their only aim is to help you help the world and enjoy doing it. Go to 80,000hours.org/upandatom or click on the link in the description and pinned comment to be sent a free copy of their in-depth career guide. Thank you to 80,000 Hours for sponsoring this episode, and thank you for watching. Bye!